But conjecture example 3 on page 34. This is the one we're going to go through for a stationary point. So it says, consider the function there, 2x on x plus 1 squared. Draw a graph. So we don't really have time to go through it, but I'm just going to bring the graph up here for us. 2x on top of x plus 1 squared. All right, on x plus 1 squared. Okay. And you'll note, what I want to point out to you is they've provided you with a V window. Whenever we're going to get you to graph in a test, we'll always give you the V window as well. Your x min, x max, y min, y max. So we'll all have the same looking graph. Okay, so 3 marks there. You absolutely have to make sure you get all the marks for a graph. All right, part B. State the coordinates of the stationary point. So stationary point means when is the slope horizontal? We can see a local max there where my mouse is at the moment. So I'm going to G-solve that max, and we've got when x is 1, y is 0.5. So we get a mark just for stating those coordinates. Don't just state x, it asks for both. All right, so we have a local max at x is 1, y is 0.5. Okay, now consider the function 3x on x plus 1 squared. All right, so they're just changing that number at the top. And this is what conjecture problems do. They just make slight alterations. Now state the coordinates of that stationary point. So I've G-solved that max. Oh, all right, so this is my answer to part B. This is my answer to part C. All right, and now we have a table, don't we? Where we have 2x on x plus 1 squared, 3x on x plus 1 squared, we have 4x on x plus 1 squared, 5x on x plus 1 squared. Okay, and we want to know what's the x coordinate, what's the y coordinate of those stationary points. So we've already done this function, we saw it was 1 and 0.5. We've done this function, we saw it was 1 and 0.75. We haven't done these two yet, so I need to graph those ones. Already, when we're doing these what we would call inductive cases, we can start to anticipate what's the rule going on here. When I G-solve that max, I can definitely see a rule for the x value. The y value is a little bit harder to see. And then we'll put a 5 in there. Okay, and 1, and this is 1.25. Can anyone see? So that's the fill in the table, you get a mark there. Make a conjecture about the stationary point to the function h of x. All right, so about the coordinates of the stationary point. So my conjecture is going to be, well, my x value is 1. All right, and they're saying, how about if you have the function ax on top of x plus 1 squared? So they're telling you this a value is what we've changed. So this number is somehow related to this y value. Can anyone see it?
Is it a over 4?
Very good. It's a divided by 4. All right, so if you have 2 divided by 4, that's 0.5. 3 divided by 4, 0.75. 4 divided by 4, 1. 5 divided by 4. Very good. It is a over 4. But don't fear. Even if you can't see this, we can prove it, and then we can come back and fill it in. So let's show you how. And this is actually not too hard a conjecture to prove. So, prove the conjecture. Well, this is the function we have, ax on x plus 1 squared. Now, we want to know, when do the stationary points occur? Stationary points occur when the first derivative equals 0. So all we're going to do is find the first derivative of this and make it equal 0. So I've got u dash, v dash, this is just chain rule. Okay, smash it together. So quotient rule now, u dash v, take away u v dash, all on top of v squared. Now, we're interested in the stationary points which occur, so we should make the argument, stationary points when h dash of x equals 0. So we're interested when it equals 0, and because it's a rational function, we're just going to keep hitting this over and over again. Because it's a rational function, we're only interested in the numerator. We just disregard that denominator. So we're interested in this equation here. Okay, so if I'm going to solve this, you can expand it, but always look, can I factorize anything? And a is common, and so is x plus 1. So if we rip that out the front, if I pull a times x plus 1 out the front, okay, this term is just going to be left with one lot of x plus 1. All right, if I expand that, I'll get that. And over here we'll have take away 2x. Okay, and now we're just going to apply the null factor law. A does not equal 0 because it's a number. So we have x plus 1 equals 0. Or this component, x plus 1 take 2x. And I'll fix that up. X take 2x, that's just going to be 1 take away x. So this gives you x is 1, and this gives you x is minus 1. So we have two values for x. Now, if we look at the original function, and all throughout, it says very clearly where x does not equal minus 1. This is not a solution, okay? The whole problem has detailed that to you. This is not a solution. So that means the solution occurs when x is 1. All right, that's what our conjecture was. The x value is 1. We've demonstrated that it's true for x is 1. How about the y value? Well, this is the function. And so the y value then is just going to be h of 1. If I put the number x is 1 into this equation, I'm going to have a times 1 on top of 1 plus 1 squared. Okay, that's a on 2 squared. That's a on 4. So we've gone ahead and we've got a on 4. Now, even if you can't see over here that it's a on 4, you can prove it and then take a on 4 and plug it there and see that it's true. So even if you don't know what the conjecture is or can't see it, you can still go ahead and prove it. So yeah, that's a pretty good conjecture problem. So all stationary points ones, they will pop up. They're a general function. It's like find when the first derivative is 0. All right, so I'll get you guys to fill that in for homework and have a go at finishing exercise D.1. It is